Okay, this is a popular question. A lot of students have been asking me to help them with understanding how to get the critical value in the test statistic and have said that they've been having a trouble where sometimes they get it right and sometimes they don't. Now, this question in particular that I have up here on my screen is from lesson 14. It's number 4, and it was a popularly requested question. And it gives us the opportunity to look at several different scenarios of how the version of this question could be different. For instance, you could have a left-tailed test, you could have a right-tailed test, you could have a two-tailed test. Also, in some of these, your sample statistic is negative, and in others, it's positive. So that could affect things as well as far as finding your test statistic goes. And specifically p-value. So I'm going to also talk about p-value in this. So if you've been struggling with finding the critical value, finding the test statistic, and finding the p-value, then this should be helpful to you. All right, now let's begin with this first version of this question, and we'll read the setup here. It says you wish to test the following claim, which is your alternative hypothesis. So let's start by writing out the hypotheses and making a note that the claim is falling under the alternative because that's important for your final conclusion. I started writing down the wrong symbol there. Let me fix that. This is for the mean of differences with paired data. So the default assumption is that there is no difference between the two sets of data or individual pairs on average, and the alternative hypothesis is that the difference is negative or less than 0. And this is where our claim sits. Okay, and we also notice that since it has a less than symbol, that makes this a left-tailed test. Also, because we're talking about the mean of differences, that means this is a t-test for paired data. Okay, so those few things are important to get figured out right away, where your claim sits and what kind of tails your test will have, and if it's going to be a z-test or a t-test. We've determined that it's a t-test because it's paired data. You can also notice that if you go to the formula sheet for test statistics down here where it says dependent paired for the mean of differences, we are using the t-distribution, and here is the formula for your test statistic. All right, and somewhere else that you can look for help with what to do is this page about t-tests, where you can see there's some help for if you have a left-tailed test, or if you have a right-tailed test, or you have a two-tailed test. And for each of those, I've given notes on how you're going to find your critical value and p-value. So this can be a lot of help too. Okay, so this is a left-tailed t-test. So we're going to be looking in this area here. Let me take a snip. Okay, we're going to be looking at that because it's left-tailed. And we're going to be using, as I mentioned before, this formula here for our test statistic. Make that better. Okay, so we're collecting all the important information, formulas, etc., and then we're pretty much ready to start sketching our hypothesis test. Make this neater. Okay, so now we are also going to be given some sample data, but let's begin by setting up our rejection region, the critical region. So we're going to do, let's do a sketch. We'll set up our sketch first. We've determined that since this is a claim about the mean of differences for paired data, this is going to be a t-distribution, the mean of 0 in the center. And then somewhere in the problem, they'll give us the significance level. So here we have 0.01 as our significance. So let's write that down. So alpha is 0.01, okay? This is the critical area. And since this is a left-tailed test, we're going to draw it on the left side to the left of 0, which means it's going to be a negative t-score, okay? And we'll find out what that value is by using the area alpha 0.05. Okay, so now to do that, notice that it says right here for critical value for a t-test, we're going to use t dot inverse. We're going to put in our alpha and our degrees of freedom n-1. So we're going to need the sample size. So somewhere in this, we should be given a sample size. Here we have 81. Okay, so with our n of 81, I'm just going to write some sample information here. Or I'll say sample statistics, since they didn't give us the actual data. They just gave us some values. N equals 81. So that means that our degrees of freedom will be 80. So we're going to do, for our critical value, we're going to do t dot inverse with our alpha of 0.05 and 80 degrees of freedom. Now, notice that I did get a negative answer. That's what I want. It's important. I can't stress this enough. To make the sketch, realize that 0 is in the center and that your horizontal axis are t-scores. So if you have a t-score to the left of 0, it has to be negative. So for a left-tailed test, your critical value should be negative. Okay, that's very, very important. And this will help you also figuring out your test statistic and what your p-value should be. All right, now that we have our rejection region set up, we want to look at the sample statistic. So this would be the sample mean for the differences. So here they've told us that the sample difference, d bar, is negative 4.9, and the sample standard deviation of the differences is 33.6. So we want to write those down for our sample statistics. The sample mean, make sure I got the right color here. I do green for my sample statistics. I do red for the critical region, and I do blue for everything else, just to help me visually. So d bar is negative 4.9. Okay, and the sample standard deviation, now notice that the sample standard deviation, that's not sigma. Sample standard deviation is known instead of sigma, so that's why we're doing a t-test, and it's 33.6. All right, so now that I've got my sample information written down, I can now take my sample information and use it to convert my sample statistic, my d bar. I'm going to convert that into a t-score. Okay, so I'm going to do that by doing d bar minus mu sub d. The mu sub d always comes from your null hypothesis, and then divided by the standard error, which is the sample standard deviation divided by the square root of n. So you've done something similar to this in other examples. Okay, so let's go ahead and calculate this. I'll just do it down here because we have a little more space that way. Okay, so I'm going to take my test statistic, TS, which is a t-score in this example, is going to be, I want the top to be separated from the bottom. I just feel like it's easier to make sure everything comes out right that way. Then I'm going to do d bar, which is negative 4.9, minus the sample, or I meant to say the population mean in the null hypothesis is 0. And then in the bottom of my calculation, I'm going to do the sample standard deviation, 33.6, divided by the square root of 81, which is my n. Okay, now this is what it should look like when you type it. It's also right here. You need to pause it and write that down. All right, so I'm doing that. Now let's go ahead and calculate it. So this is my test statistic. Okay, this is my green boundary. So my green boundary is going to go, because it's negative 1.3, in this case it ends up being outside of the rejection region. That's my test statistic. Okay, notice I use a little star to note my test statistic. Then my area to the left of this, all the way into the tail, is my probability of getting this test statistic, or one that is even more far away from 0. So that's why we call this P for probability, p-value. Okay, so the area there is a left area. Now notice that right here it says p-val equals t dot dist, your test statistic, which is a t-score, your degrees of freedom, and 1 for cumulative. So I'm going to do that here. Where shall I put it? I guess I'll put it up here. T dot dist with my test statistic. I'm just going to click on it here. My degrees of freedom, and -1, and 1 for cumulative. All right, so there's my p-value. Okay, and now I can compare the two areas. I can compare the red area, alpha 0.05, with the p-value area 0.097, and see that the p-value is too large to think that my null hypothesis is incorrect, right? We always say if the p-value is low, then the null must go. So we would fail to reject the null hypothesis here. You could also say that since the test statistic did not fall in the red region, or it's not farther away from 0, it's not more extreme than the critical value. For those reasons as well, we would fail to reject the null hypothesis. All right, now that was for a left-tailed test. Let's look at a different tail. Okay, so now we want to look at right-tailed. So let's see what happens with the right tail. Okay, so now we have the null hypothesis that the mean of the differences is 0. In other words, there's no significant difference. The alternative hypothesis is that the difference is positive or greater than 0, and they've told us that the claim is contained in the alternative hypothesis. And we know that since it is I'll use another color here, I like purple. Since this is a greater than symbol, that means this is a right-tailed test. And because this is a test about a population mean where sigma is unknown, and why is sigma unknown? Or you could also just say it's paired data. Whenever it's paired data, it's going to be a t-test. Or anytime it's a claim about a mean where sigma is unknown. Okay, because we know S instead of sigma. Okay, we know the sample standard deviation, but not the true population standard deviation. Then that makes this a t-test. Okay, now we are once again going to use this formula because it's a t-test for paired data. Okay, and then we're going to look at our t-test page. Here's our t-test page again. And this one's a right-tailed test. So we need to make sure we're careful when we're calculating our test, our critical value and our p-value. All right, now we're going to need some information, the sample information. Actually, I think I'll write this here. I'm going to take the sample statistics and then convert them into a t-score, a test statistic. Test statistic. And so we're going to want the sample size, we're going to want the sample mean of the differences, and we're going to want the standard deviation, the sample standard deviation. So all that should be given. We should also be able to get our significance level for the critical region, for the rejection region. Alpha equals something, and then the critical value will come from that. All right, so let's look back at our information. We were given an alpha of 0.02. Okay. We were given some sample stats here, 120 for the N, the D bar, the sample, hang on, get this figured out. Got myself all mixed up here. I think I just need to make this half and half. There we go. Okay, so this is N equals 120, D is 3, and I'm going to change my color to be consistent with number of categories. It helps if you want to use colors. You can use green for your sample statistics. D is 3. The sample standard deviation is 13.3. Okay, so now we have everything we need, and we are ready to start sketching this distribution. So we always have a bell curve. We always have a bell curve with a mean of 0. The question is it Z or is it T? Well, because this is a paired test for about a mean where sigma is unknown, this is a t-test. We are doing a right-tailed test, so our critical value will be on the right, so that makes it a positive t-score. And the area to the right of that is all of alpha, which in this case is 0.02. So notice that where it says critical value is going to be t dot inverse 1 minus alpha, okay? Because 1 minus alpha is the area, let's get a color here. Let me see. Okay, this area over here is 1 minus alpha, right? Because we know the total area under the curve is 1. So if the right side is 0.02, then this side must be 0.98. And remember that the distribution functions like t dot dist or t dot inverse is always going to assume that you're giving it a left area. So that's why we're going to use 0.98 instead of 0.02. So we're going to do t dot inverse 0.98 with a degree of freedom. Our n is 120, so the degrees of freedom would be 119. Okay, so there is our critical value. Now make sure that it's positive because it is to the right of 0. It's a boundary to the right of 0, so it should be positive. Now let's say you made a mistake and you did t dot inverse and you put in the 0.02. Then you would get the same answer but just negative. Now if you're drawing your sketch, like I've tried to urge you guys to draw your sketch every single time, because looking at this sketch, I should understand that my t boundary should be a positive value. So even if I made a mistake here, I could easily just change the sign on that and I'd be okay. All right, so just paying attention to your sketch makes a big difference. So that's our critical value. Now we'll take our information from the sample and standardize it into a test statistic t-score that can be compared with this t-score. Right? So we're going to take the numerator, we're going to do d bar 3 minus the mean in the null hypothesis of 0 divided by, in the denominator, I want the sample standard deviation 13.3 divided by the square root of n, which is 120 here. Okay, so this is what it should look like here. And then when you calculate it, this is what you should get. That's your test statistic. Okay, now we'll put it on the sketch in relationship to the critical value on the horizontal axis. So 2.471 would be in the red region. 2.471. There's my test statistic. So it seems that my sample statistic is farther away from the mean than the critical value. It's more extreme. So this would lead us to reject the null hypothesis in this case. Now, this green area in the right tail is our p-value. So what are we going to do? Right here it says p-value equals 1 minus t dot dist. Why is that? Because when I do t dot dist, let me show you. T dot dist, actually let me do it up here. Maybe I'm going to do it right here. So t dot dist on my test statistic 2 point, well, let's go ahead and instead of typing it in, I'm just going to click on the calculated value here. Okay, and then my degrees of freedom, again, 119, and then true for cumulative. Okay, so now when I do that, look at this area it gives me. That area is huge. Remember, the total area under the curve is 1, and that is certainly not possible to be this little area here. So hopefully, even if you weren't paying attention to the directions here that said 1 minus t dot dist, if you're doing your sketch and you're looking at that little green area and this number and you're thinking, that doesn't make sense. Let's subtract it from 1 and get an answer that does make sense. And now you can see comparing the p-value to the alpha, the p-value is low, so the null must go, right? All right, so that's how you do a right-tailed test. Let's also look at a two-tailed test. All right, and so again, we see that the claim is in the alternative hypothesis. Let's go ahead and draw this out. So the null hypothesis is that the mean of the differences is equal to 0. The alternative hypothesis is that the mean of the differences is different from 0. So in other words, the null hypothesis is that there's no significant difference between the two sets of paired data, but the alternative is that there is some difference. We just haven't specified if we think it's going to be greater than 0 or less than 0. We just think that it's different, right? And that's our claim, right? And this symbol tells us it's two-tailed. And again, because we are doing a claim about a mean where sigma is unknown, I'm trying to change the color here, folks, okay? Or because it's paired data, that's another way you can remember paired data tests are always t-tests, right? So that's why we know that when we draw our distribution curve to sketch everything out, it's going to be a t-distribution. So everything we do here is going to be t dot dist, right? And we're going to be doing a two-tailed test. So we're going to use this set of instructions. Okay. And where can I put that? I don't know. I haven't liked where I had it before. So we'll just keep it up here. All right, now, what about the critical region? We're going to need the alpha, which is our area, which is given in the problem somewhere. 0.02 given again, okay? So 0.02. But we are going to do a two-tailed test. So now we're going to have a negative critical value and a twin positive critical value. And remember, your bell curves are symmetric, so you only need to find one of these and then change the sign to get the other one. So this negative t-score is going to be found using t dot inverse on alpha half. Why is that? Because the total area in both of our tails is 0.02. But if we're splitting it up into two tails, then alpha half is 0.01 on this side, and over here we have another alpha half of 0.01 as well. Okay, so we're going to do T dot inverse 0.01 degrees of freedom. We need our N. N is 64 here, so it's going to be 63 degrees of freedom. And here is our negative critical value. And the positive one is just going to be the opposite sign of this one. Right, so that's it. We're done with our critical value. Make those red. And our critical region is set. So we've set all of the, we've set the bars, right? We know where we are trying to get to in order to reject the null hypothesis. And then we start looking at the sample data. So the sample data, let's go back and collect that. Sometimes they give you the data and sometimes they give you the stats. Okay, so N, D bar, or X bar, depending on the problem, and your sample standard deviation. Let's go here. We have 64 for N. We have negative 17.6 for the sample standard deviation and 45.3 for the wait, what did I say? Let me say that again. We have negative 17.6 for the sample mean of the differences, and we have 45.3 for the sample standard deviation of the differences. And so now we're going to use the same, sorry, my reminder that I have to start office hours just went off. I was just about to say we're going to use the same test statistic formula since we're still doing a t-test for the mean of differences. So now we will take our sample mean, the d-bar, and change it to a test statistic that can be compared to the critical value. So we do the d-bar 17.6 minus the mean in the null hypothesis. Now I know you're thinking, well, it's just 0, so it doesn't change anything. Yeah, but that's not always how it is. That's how it always is with paired data, but if you're doing some other problem where it's not paired data, you probably will not see a 0 in your null hypothesis. So just always look at your null hypothesis to know what value you should be using for your mu. And then in the bottom, we have the sample standard deviation 45.3 divided by the square root of n, which is 64. Okay, so that's what it should look like, right? Then you get this answer. So there is our test statistic. That's our test statistic. Now, where does the test statistic go? In relationship to the critical value in this example, it happens that the test statistic falls in the rejection region over here. Because it's more extreme, it's farther away from 0 than the critical value is. Right, now I'm just going to adjust my labeling here. Oh, I guess we can't do it like that. I'll just draw a different arrow here. Okay, so the whole red region is the alpha part, and then our p-value, the probability that matches the test statistic, that is, now here's the trick that a lot of us miss. Because our alpha is split up in half, so is our p-value. So that means that even though you technically don't have another test statistic, you can picture another ghost test statistic of positive 3.108 over here on the right. So this just can, if you draw it like this, it might help you to understand what's happening better here. So this is the other half of your p-value, okay? Okay, so if you find this area over here, you just need to double it. And notice that it says p-value equals 2 times t dot dist, right? So for the p-value half portion, we're going to do t dot dist with our negative 3.108, and our degrees of freedom is 63, and true for cumulative. So there is half of our p-value there, and we have another one of those over here, and it's not negative because remember, probabilities can never be negative. They're just the same area on both sides. So you add those together, or in other words, you multiply that by 2, and you get your total p-value. So your total p-value, whoops, is t dot, or I'm sorry, 2 times what you found with the t dot distribution. Okay, that's the trickiest one, is the two-tailed test. And that's probably why sometimes you're getting it right, sometimes you're not, because the tails of the test are going to affect how that all plays out. Now there's one more thing to consider. Here's another two-tailed test, but my sample mean is positive here. So that is going to change things a little bit. Okay, so let's write out some things. We see the mean, get my blue back. Okay, so we see the null hypothesis, again, is that the mean of the differences is 0. The alternative hypothesis is that the mean of the differences is different than 0, and that's our claim. Why do we know this? Because it says so right here. Other times you have to look at how the claim is worded and determine if there's equality in it, but that's for another lesson. We're focused on understanding how these different tails play out here. And then we see, again, that we have the two tails because of the not equal symbol. Okay, let's also write down our critical value, alpha. That's not our critical value, that's the critical region area, right? Which is given here as 0.05 in this problem. And then we need our sample information, sample stats, d bar, well, let's start with n, sample size, the sample mean, and the sample standard deviation. Now, in some problems, they might give you the actual data, the two pairs, and you have to subtract them to get the differences, then use the average function to get the d-bar, and the stdev.s to get the sample standard deviation. So I'm not going to go into that here. I went over that in one of the, I think it's the last question in lesson 14. The video should explain that pretty well, hopefully. Let's see, so 49.3. Okay, now got all our information mapped out here. So we're going to sketch the distribution. Okay, so we've got our curve, which is a t, and we've got our alpha going to be split up on two sides again. So we have alpha half is 0.025, that's half of 0.05. And on this side, the positive critical value with an area of alpha half equals 0.025 again. So to find our critical value, okay, notice again, we're using this. Let's just put this in the middle here. Okay, so the critical value, it's easier to find the negative one. So we're going to go t dot inverse on alpha half 0.025 with 57 degrees of freedom. So there is our critical value. It's it's negative like it should be. Make sure you're always paying attention to if the signs match what your picture is saying, okay? And then you would have the positive one over here, twin brother, just positive. All right, and we're done with our critical region. Now we start looking at the sample data and we convert this into a t-score, again using this formula. Okay, so the test statistic is the d bar 13.6 minus the mean from the null hypothesis of 0 divided by the sample standard deviation 49.3 divided by the square root of n, which is 58. Okay, so this is our test statistic right here. All right, and where does it go on our sketch? In relationship to this critical value, it's just a little bit past it, so it does fall in the rejection region. We would reject the null hypothesis here, right? So right in here, just barely made it. Our test statistic is, well, now notice that it's positive. So this would actually be on the right side, 2 point, whoa, 2 point, let's see, 2.1, 2.10, right? So I'm going to write that over here, 2.10. There's my test statistic. The p-value is half, and the half of the p-value is the area on the right. The other half of the p-value, even though there's not technically another test statistic, you can just pretend that there's another one over here. It's like a ghost version. And that's the other half of your p-value. Now, which area is going to be easier to find with t.dist? It's going to be the one using the negative value. Now, if you use the positive test statistic here, let me show you what happens. If you do t.dist on your positive test statistic 2.10, again, the degrees of freedom was 58 minus 1 is 57, and 1 for cumulative. Now watch what happens. You see this? It's huge, right? That can't possibly be this little green area. Again, it's very important to draw your sketch and try to make sense of what your numbers are saying. That can't be right, right? It has to be 1 minus that amount, right? 0.02008. Now, if I had done that same thing over here with the negative version of my test statistic, t.dist, negative 2.10 with 57 degrees of freedom, I got that same p-value, oops, right? I got that same area right over here. I got the same thing, just using the negative version, okay? So whatever you do, just make sure that you're paying attention. Does your answer make sense? And then total together, these two areas added together, or this area times 2, is your p-value. So that's why it's 2 times what you get from the t.dist, right, for two-tailed tests. Very important. So I know that was a really long video, but there is no other way to rush understanding why you're sometimes getting these right and why you're sometimes getting these wrong. There can be other examples that we do where you would be using different formulas from this packet, you know, so you have to kind of make sure you're paying attention. Is it one sample mean where sigma is known and you're going to be doing z-scores, and you've got, you know, z equals something over here. Also for your critical values, the alpha half, if you're doing a confidence interval, is going to be one sample mean mu where sigma is unknown, and then you're going to be doing a t-table, a t-distribution situation again, or is it one sample for proportion p, which is always using the normal z's, right? So you just have to really look at your formulas, look at your formula sheet, pay attention. The other thing I didn't mention is just why it matters where your claim sits, but I think that is something for another lesson. So I'm going to stop the video here, and I hope that